So my name is Netanel Shpigel. I'm from Professor Doron Orbach Group here in Bar-Ilan University. And today we would like to talk on the use of highly concentrated aqueous electrolyte solution for high voltage lithium and beyond lithium ion batteries. So here maybe the term high voltage is not the most accurate, as we all know that in a aqueous solution we can never get a high voltage like in non-aqueous solution. But considering the limited potential window of water which is 1.23, we can provide much more extended potential window by using concentrated electrolytes, as I will show you. So why aqueous batteries are interesting? We are thinking about large energy storage. And in large energy storage, we should use large amount of mass, large amount of batteries, and large amount of electrolyte as well. So in this case, we cannot use flammable electrolyte, and we should also consider the cost of the electrolyte. So for this, water electrolyte may be the ideal solution for large energy storage. However, we all know that water electrolyte has very poor electrochemical stability, and we are limited to about 1.2, 1.3. So for this reason, for many years, you can see here the publication about the aqueous battery. So since the invention of or commercialization of the lithium-ion battery, there are no many publications, and I would say this field was quite exotic. But I think that the big leap was obtained in 2015 with the publication of the water and salt concept. Water and salt means to use highly concentrated aqueous electrolyte, and as you can see here, you can get much wider electrochemical window from 1.23 to 3 volt and more than 3 volt by using aqueous concentrated electrolyte. How it works? So basically, if you have a high concentration of salt, you have less water in the solution, so you have less active parasitic species, let's say, less water that can interact and decompose. And second, even in highly concentrated electrolyte, the remaining water molecules are confined and strongly bonding to, in the first elevation shell, and strongly bonded to the cation or to the anion. Also, as you can see here, when we increase the concentration, if we're speaking about anodes, when we increase the concentration, you have we call it quasi-inertial shift. It means that the redox peaks are moving to the more positive potential away from the water splitting potential. And finally, in some organic soluble salt, you have also SEI-like formation. So you have passivation on the anode, which further suppress hydrogen formation. So the most studied water and salt, at least for lithium electrolyte, is the 5 molar or 21 molar lithium TFSI. For sodium, for example, there is a sodium perchlorate salt, which in a concentration of 10 molar. But speaking about lithium TFSI, it's completely impractical because you can see here it's extremely expensive electrolyte, and I just made some rough calculation. You can see here lithium hexafluorophosphate, the conventional electrolyte for lithium-ion battery. It's about $1.6 per 1 ml, while lithium TFSI is about $10 per 1 ml, so clearly it's not practical for large energy storage. So here we want to suggest some alternative electrolyte systems which are also very stable and cost effective. So the first system is the lithium chloride 14 molar. It's one of the most soluble salts. It can reach even a 40 molar concentration. And what you can see here, looking at the potential window, the green line is 1 molar, while the dark line, the black line, is 14 molar. You can see here that we significantly increase the stability of the electrolyte decomposition. Here it's hydrogen formation when we increase the concentration of the electrolyte. So we decided to test this concentrated electrolyte for two systems. One is the Maxine electrode, which is here. It has capacitive type response. You can see here the rectangular shape. And what you can see is that 1 molar you have parasitic current in both negative and positive side. Here it's due to titanium oxidation. Here it's to hydrogen formation. While in concentrated electrolyte you can get wide potential window without any significant parasitic reaction. We also tried to test this electrolyte in a several phase molybdenum sulfate anode. And what you can see here is that in 1 molar, only this peak can be obtained, while the second peak of Shpigel cannot be obtained because the hydrogen generation, and this is why it appears in a dashed line. And in contrast, when we use 14 molar of lithium chloride, we got a significant shifting of the redox peak. You see 280 millivolt to, and then also the second intercalation peak can be achieved without any water splitting. So this gives us the idea why not to combine them. Now we expand the voltage window of the Maxine and shift the potential window of the Shpigel, so we can make like integration between both. And indeed, this is what we made. So we take the advantage that Maxine is 2D material with good electrostatic properties, and we encapsulate Shpigel particles between the Maxine sheet, and we get like very nice, flexible, and freestanding electrode without current collector. So here you can see the performance of this system. You can see here the CV is a simply combination between the capacitive type response and the contribution of the Shpigel redox. And basically what we can see by playing with the concentration or the mass fraction of the Maxine, of the Shpigel in the Maxine, we can get an optimum value of both energy density and power density. I will not get into much details, but this is an interesting calculation, how you can calculate exactly what the contribution of each fraction. But anyway, we get very good cyclability for this system. So this is the first alternative for the lithium TFSI. Now I want to speak about non-lithium system. This is another interesting system. Here we're speaking about concentrated sulfuric acid. So it's well known for many years that the bisulfate can be inserted into graphite. But still this study, no one considered it as an option for energy storage. And what we did here, we tried to increase the concentration of the bisulfate, because we know that at high concentration only the first dissociation of the sulfuric acid is occur, and hence we're increasing the concentration of the active species of the bisulfate, but at the same time we reduce the concentration of the water. So here you can see that indeed in 5 molar you cannot get any significant reversible capacity, while changing to 70 molar we can get perfect intercalation of bisulfate into graphite. And just mentioned here, graphite is not anode, it's cathode, because it works with anions. And you can see here also that the capacity in this 70 molar was 80 milliampere hour per gram, and here we have a ratio of 1 bisulfate per 20 carbon atoms. Okay, so the performance of the half cell of graphite, you can see that it works, it has a very fast rate capability performance. There are no dramatic difference between a 1 C rate to 15 C rate. Very good cyclability, which is very surprising because we are working with 70 molar sulfuric acid. It's a very corrosive environment. And the only question is which anode can be suitable to this system, how we can make like a full cell. We tried many carbon, but no one gave us a stable response. So instead, we chose the MXene electrode. MXene is well known that it works it has pseudo-capacitance response in sulfuric acid, but obviously no one tried it in 70 molar sulfuric acid, so we tried to see if it works in sulfuric acid, and you can see here we also got this inertial shift, but we see that the capacity is more or less remains the same when we varied the concentration, and we could get something like a 70 milliampere hour gram, which is comparable to what we got with graphite. And here you see the full cell. So basically the mechanism is dual ion. You have insertion of bisulfate to the graphite, oxidize the graphite, and in the same time, simultaneously, we have insertion of proton into the MXene. And you can see here that we got also very nice cyclability. And this is another example for beyond lithium battery, which work on sulfuric acid. The last system, I will just describe it shortly. It's about sodium-ion battery. So here we work with NTP, sodium titanium phosphate. That's very nice plateau in a concentrated 10 molar sodium perchlorate electrolyte, about minus 0.7 versus HAGCl. And here the idea, we have the PVDF binder, which is inactive mass. So why not try to change the binder to some active binder? So here we use, again, MXene. MXene has good binding capability, it has electrostatic interaction, and we was able to increase the mass loading of the active particle up to 80% of the electrode. And you can see here the black line is the NTP with the PVDF, and the pink line is the NTP with the MXene. And you can see that we got a significant increasement in the capacity due to the fact that MXene is binder, but also has some capacitive type response. And in this we can get very nice cyclability. In fact, I think we got more than 2,500 cycles, but here we present only part of the cycles. So some take-home messages. So I showed that the electrochemical stability of the water can be significantly expanded to up to 3 volts. This wide potential window enabled introduction of new anode and cathode. Don't use TFSI if you want to go to practical application. It's good for paper, not practical. And alternative and cost-effective electrolyte should be developed. And this is general note, more focus should be set on development of a system for large energy storage. And here I want to thank to all my friends in the lab, and thank you.